In the PowerPoint today, what we're going to go ahead and do is we're going to be filling out our packet to get ready for our round robin tomorrow. So during the course of the PowerPoint, feel free to fill out your packet or go ahead and take notes in your actual notebook. We're first going to talk about the definition of work and how work is different than the definition that you would find in your everyday life. Work specifically is a force applied over a given displacement. Taking a look at the picture, what's happening here is the individual is applying a force to the cart, and there is a force in the direction of motion. Notice that he is pushing down and to the right. The only force that we're really interested in is the force that's actually to the right. Key in this definition is that the object must move. If the object doesn't move, according to the physics definition, no work can be done. The second point, again, there must be some component of force in the direction of motion. Taking a look at the picture once again, the mother is pushing the child down and to the right. Notice that there are two components here. There's an X component and a Y component. We are only interested in the X component, the component of force in the direction of motion. The equation for work is force times displacement. Once again, if there's no force, there can be no work. If there's no displacement, there again can be no work. You need both the quantities to actually contain a quantity of work. The units for work, if you do a dimensional analysis and apply the units for force, that would be a Newton. You apply the units for displacement, that would be a meter. So the units for work would be a Newton meter. If you were to expand out a Newton, once again, is a kilogram meter per second squared. When multiplied by a meter, it becomes kilogram meter squared per second squared. Probably the easiest way to display your unit for work is to call it a joule. Any of these is appropriate, but again, probably the easiest way to go, provided everything's in standard SI units, is the unit for joule. Taking a look, let's apply the definition to one of the following scenarios. The question is, which of the following is work done? In scenario A, you have an individual that's pushing a box to the right with some applied force, and the box is moving. In scenario B, you have a man who's just standing holding change. In scenario C, you have a waiter who's bringing out dinner to the individuals. So again, think about which one you think work is done. The correct answer is A. B, there is no work done because the individual does not move. Obviously A is the answer, or at least one of the answers, because there's a force applied and then the cart does experience some type of displacement. In answer choice C, you'll notice that the individual is moving and does apply a force, but let's take a closer look. The applied force is up while the displacement is to the right. If you recall our definition of work, there must be an applied force in the direction of motion. So what's happening here is the applied force is up. There is no applied force to the right since the waiter is holding the tray from the bottom. Once this box is moving, there is no force to keep it moving. That's Newton's first law. So in this scenario, this is probably the most common scenario where an object would move, there would be a force, but there would be no work done. It's when those two things are perpendicular. Transitioning into energy, energy is the ability to do work, which means that if I have an object that has energy, it can apply a force over a given displacement. Two of the types of energy are gravitational potential and kinetic. Gravitational potential is the energy due to position in a gravitational field, whereas kinetic energy, based on the picture, is the energy of motion. Taking a look specifically at the equations for potential energy, the most common type is gravitational potential, and will be the only one we'll deal with in this chapter. Gravitational potential energy, once again, is the energy due to position in a gravitational field. The gravitational field is G, and for the purposes of this equation, we will plug in not negative 9.8, but positive 9.8. So potential energy is based upon three quantities: the mass, the gravitational constant, and the height above the ground. So if you were to have a more massive object 1 meter above the ground, that would be a greater potential than something that would be half a meter above the ground or half a kilogram above the ground. So they're all in direct proportion. If you increase mass or height, you will increase your potential energy. Once again, the unit for this, much like the unit for work, is a joule. So there'll be some equivalents that we'll come up with here in a minute. The second equation we're going to take a look at is kinetic energy. Kinetic energy is 1/2 mass times velocity squared. The mass of the object definitely matters. The velocity definitely matters. But there's a greater dependence on velocity than mass because the quantity in the equation for velocity goes as a square. So if you were to double the mass, you would double the kinetic energy. If you would double the velocity, you would actually experience 4 times the kinetic energy. Once again, the unit is joule, and we'll go ahead and make the connection between work right now. Probably the most important thing for our round robin tomorrow would be the work energy theorem. The amount of work you do equals the change in energy for any given object. For example, if I were to place an object from the ground onto a table, the amount of work I do, the force over a given distance or displacement, would equal the energy I would give the object raising it to the table. The same is true if a car was traveling toward me with some kinetic energy. As the car travels toward me, I would be taking away the energy. The amount of work I do would equal the energy I would take away from the car. Probably one of the more important things in this chapter that will lead us into most of our problems is the idea of conservation of energy. Not so different than the law of conservation of mass in chemistry. We have the idea that we cannot create something, we cannot destroy it, we can only transform it from one form to another. In energy, as it is conserved, the amount of total energy will always be constant. Taking a look at the pictorial here, you'll notice that in each picture, when adding both the kinetic and potential energies, we get a total of 50,000 joules. While that is the total energy and it is constant throughout, each individual energy could be different. Taking a look at the first picture, the kinetic energy is 0 because the object is not moving. It has all potential energy, and as long as it has height above the ground and mass, it will have potential energy. As the object begins to fall, you'll notice that the kinetic energy is increasing while the potential energy is decreasing. This makes sense based on our equations because potential energy is height-based, and it's losing height. In response to the loss of height, we are gaining potential energy, we are gaining speed. As it continues to fall and gets to a spot down here, once again, we have a loss of potential energy in response to that, a gain in kinetic. The amount of potential lost equals the amount of kinetic gained, so that once again, the addition of both numbers still gives us 50,000 joules. Once the individual reaches the ground, all of the potential energy has now become kinetic. And again, looking at the equations, potential energy is height-based. There is no height, there can be no potential energy. But again, if energy is conserved, the total must still be 50,000 joules. So to summarize, what we have is the idea that total energy must be constant. It's always 50,000. It's just a matter of what type of energy it has, kinetic or potential. Taking a look at this picture, this is a Rube Goldberg machine. Rube Goldberg machines are elaborate setups to do something very simple. If you read down here, this is an idea for dodging bill collectors. The tailor is calling off the measurements to a stock boy. The stock boy mistakes the measurements as football signals and tackles the dummy. Following the energy conversions here, the dummy will push the paddle. Pushing the paddle pulls the bottle off the top of the shelf. It has height, so it has potential energy. As it falls, that potential energy goes to kinetic energy. As that falls and hits the compressor down here, it compresses open, knocking the cabbage off the table into the basket. The cabbage, having height above the ground, has potential energy, and when it falls, it goes to kinetic. The cabbage falling to the basket will close the scissors, which in turn will snap the string, causing the sack to fall. Again, it has potential since it has height. As it falls, it goes to kinetic energy. In the last case, as we take a look right here, the sack falls onto the scale. One side decreases in height, the other will increase in height, pushing the cement that's located in the basin at the top on top of the bill collector. Once again, on top, it has potential energy. As the cement falls onto the bill collector, it goes to kinetic energy. And at this point, you do not have to pay your bills because you just put the bill collector in cement. Taking a look at the last slide, again, probably the most important thing would be the work energy theorem, how work is related to energy. So let's take a look at the following scenario. You have a diver on a diving board jumping into a pool of water. Presently, he has height above the ground, so therefore he has potential energy. As he begins to jump, the potential energy transforms itself into kinetic energy. The kinetic energy at the surface of the pool is at a maximum because, again, he has no height at the top of the pool. All the potential has now gone to kinetic. At this point, the energy has to go somewhere, so in order for the energy or kinetic energy to leave, work must be done. The water is applying a force over a given displacement, causing the diver to slow down. The key question here is if the man starts with 100 joules of potential energy, what is the work done by the water to slow the man down? If you understand the work-energy theorem, the amount of work done equals the energy change in something, the answer is 100 joules because, again, if he had 100 joules to start with, the energy is taken away by the term for work. So 100 joules of work is done by the water. At this point, you've filled out your sheet. If there were any topics or terms you did not get, go ahead and consult the text. Feel free to use anything online. We will review a couple of the topics before we get started. Review a couple of your questions if we have them. But this is the background information you need to complete the round robin.